Morning, everyone. Questions while we wait for others? Yeah, I can believe. I think it's hard for everyone, motivation-wise. My suggestion is to move away from the computer. Move away from the computer. If you have a physical copy of the book, that's perfect. Do some exercises from there. If you don't, then jot down questions from one of the free online resources and do them away from the computer. I think the computer, too much computer is not a good thing. Morning, Chloe. Yeah, I mean, it's a bad situation overall. I'm sort of well aware of that. You know, maybe also, maybe do some sort of break, you know, after class, go for a walk, just half an hour, just put that behind you, and then you can start doing some exercises or whatever you want to do. Oh yeah, second semester is officially all online. It's been announced quite a while back, and I mean, things in Quebec aren't getting any better anyways. So unless a vaccine comes along, or some sort of remedy, it's going to be online for a while. I mean, it's fine for me. I find myself working a lot more than I normally would. Not in a good way. Everything seems to take forever to do. You know, I mean, correcting exams online is very time consuming. Well, Shamir, I hope fall 2021 we'll be back to in-person, I hope. But again, I mean, if there's no vaccine, that's not going to happen. So, I don't know. Hoping that AstraZeneca is going to work out there. Yeah, that's the thing. I mean, I too am spending too much time indoors. Yeah, so, you know, I mean, even if it's just a half-hour walk after this lecture, you know, to make a clean break and try to get some normalcy back, like as if you were walking to class and going to another class and so on, and then exercises from the book. I don't know that McGill is working. I don't know that McGill is working on a vaccine. I've not heard anything to that effect. Questions in the meantime? How are we doing with critical points? Maximizing and minimizing functions? Why don't we do a few examples of that? Shall we? Oh, go ahead, Michael. Question? In the meantime, we can get started on this. We're looking for critical points. Before we do that, yeah, go ahead, Michael. Before we do that, what is the domain here? I don't know. Yeah, okay, so apparently, yes, the exam solutions are up. What is the domain? While Michael is getting his one more question. All real numbers except plus or minus 3. Right? Go ahead and take the derivative. Go ahead and take the derivative. You know what the derivative is. So there's a plane flying past the radio tower. What's the change of distance between the tower and the plane? I don't know what the actual question is, but if we have some sort of tower and you have a plane, I don't want to draw a bad plane here, but it's going to be bad. Yeah, I knew it was going to be bad. And what is the deal with the plane? If I remember correctly, I think the plane is flying at some angle relative to the horizon. Is that the idea? Far from it. It's a terrible drawing. But anyways, I mean, if the plane is flying at some angle relative to the horizon, that's the angle right here, right? And if you are looking at the rate of change, rate of change of the distance from the plane to the tower, that's the idea. So in this case, you don't have a right angle triangle, right? So maybe a law of cosines, right? In the hint, there was a law of cosines. So the triangle, exactly that, right? I mean, this triangle here is not a right angle triangle. So that's the idea. Right. So with that in mind, then you can answer the question with relative ease. Does everybody have the derivative there of q? That is not correct. That is not correct. Thank you, Jennifer. Absolutely. Denominator should be squared. There we go. Convinced? And from then on, we can simply read off the critical points. What are the critical points? Critical points, t equals t equals 0. Plus or minus 3 is tempting, right? Because that's where the derivative does not exist. However, this is why we wrote down the domain first. By definition, critical points must be in the domain. So here, plus or minus 3 are not in the domain. Plus or minus 3 are not critical points. All right, there it is. X e to the 4x. Absolutely, Shamir will do that after this one. Shamir was asking for an example where the derivative is undefined, but the critical points are still in the domain, right? So kind of like this, but where plus or minus 3 would have been in the domain. Interesting. Absolutely. Absolutely, that works. Right, so absolute value of x. Absolute value of x is a nice example there, where the domain is all real numbers, but the derivative does not exist at 0. Absolutely, that does it. But we'll see an example where you didn't start off with a denominator, and then by taking the derivative, you actually get a denominator. But let's do this one first. This is a product, so product rule applies. So you see the derivative, well, first of all, the domain of the original function was all real numbers. Exactly that, Michael, very nice. Very nice. You see that the domain was all real numbers. The derivative is defined for all values of x. So critical points are where the derivative is going to be 0. Right, because it's defined everywhere. The exponential is never 0, so we see that the only critical number, x equals, everyone? Anyone? You know what it is. Minus 1/4. Absolutely. As Michael suggested, let's take the following. Michael suggested the square root, nothing wrong with that. But let's make it even more general and consider the cube root here. Right? First of all, what is the domain? You know the domain is all real numbers, right? When you're talking about cube root, it doesn't matter if it's positive or negative. Everything is fine. And the derivative, well, you know what the derivative is. The derivative is easily seen to be this. Right, so domain, which was originally all real numbers, now we get this as the derivative, and you see that you've got a denominator here. So critical points are going to be where the derivative, thank you. It was a bit hasty there. I was missing a 3 in the denominator. Thank you, Sean. And Shamir as well. Thank you. So critical points are where the derivative is 0. Right, it doesn't matter, but I mean, of course, you don't want a wrong answer. It doesn't matter for the critical points, but you don't want to give a wrong derivative. Critical points are where the derivative is going to be 0, where the derivative does not exist. Derivative is 0 when the numerator is 0. So that occurs at 0. And the derivative doesn't exist when the denominator is 0. And that occurs at plus or minus 2. There it is. So critical points, plus or minus 2 and 0. Absolutely, Rachel. We'll be getting to optimization next week. So very nice word problems, which ask you to maximize and minimize certain things. So here we are asked to find the absolute max and min. Of this function on the interval -3 to 5. Maxwell wants the derivative of 9x to the ln x. Oh, maybe there's in fact an x there as well. Whatever, it's all the same. And I'm sure you did it, or you were doing it fine, Maxwell. Carolyn is asking for the domain of the number 40. Domain was all real numbers here. Ali is correct. Critical points for when the denominator of the derivative is 0 is still correct if the original function was defined at those points. Yes. Right? The definition of a critical point is where the derivative is 0 or where the derivative does not exist in the domain. Back to Maxwell's question briefly. You were looking for the derivative of this, and you know exactly what to do. You're going to start by taking the ln I suspect the mistake you were making is when you took the ln, you brought the power down, but 9 is not to that power. So there's my hint to you. I strongly suspect that that's the mistake you were making. We are looking for the absolute max and min of this function on that interval. You know what to do, right? You know that a continuous function on a closed and bounded interval attains an absolute max and an absolute min. Where can these occur? By Fermat's theorem, they have to occur at critical points or at the endpoints. So let's take the derivative. Let's work out our critical points. We factor out a 3x from here. We get an x minus 4. So as Maxwell suggested, critical points 0 and 4, both of which are in the interval. Excellent. So now let's look at our function. And as you know, this is the original function, right? Let's look at the original function at the critical points and at the endpoints. Whichever one is largest. So when x is 0, that's easily seen to be 5. When x is 4, that is minus 2 times, minus 2 times 16 is minus 32 plus 5 minus 27. I want to say minus 27. Is that right? Thank you. At minus 3. Minus 9 times minus 81, minus 76. And here, minus 20. Are these correct? Would it be wrong to say the endpoints are critical points? Right, because because the derivative doesn't exist there, right? I mean, I suspect that's where you're going with that. And, you know, I would have been tempted to call them critical points as well for that reason. Nobody does, though. Nobody does. Everybody calls them endpoints. And the thing is that, you know, we don't have any information about our function on the right of 5 or on the left of minus 3. So you could define a right-handed derivative and left-handed derivative, which would make a lot of sense here. The book discusses that a bit. We don't. But that's why you wouldn't call them critical points. Well, first of all, are these correct? I'm not suggesting that they are. Well, I mean, they could, look, I mean, let's not worry about that, because I mean, it's a subtlety about endpoints being critical points or not. I mean, by definition, if the derivative is 0, and it happens to be one of the endpoints, then we'll call it a critical point. That's no issue. But I think the point Jennifer was making was, should we also treat -3 and 5 as critical points because the derivative does not exist? And I'm suggesting let's not do that. The answers are correct. Very good. All right. Well, I mean, let me share with you how I was able to work these out so fast. It's just using properties of mathematics, right? If you plug in 5, this is 5 cubed minus 6 times 5 squared plus 5. And if you're just looking at these, factor out, right, this 5 cubed treated as 5 times 5 squared. And now, factor out 5 squared. So this is 5 minus 6 times 5 squared. And that's just -1. And you know that's 25. So that's -25 plus 5 is -20. Right, so this thing you can do in your head, right? Just take a 5 out. 5 minus 6 is -1 times 5 squared. And you know, I mean, it's going to work for all the other values. Right, you have 4 cubed, which is 4 times 4 squared, minus 6 times 4 squared. So you just get -2 times 4 squared. So you get -32 plus 5 is -27. Well, so let's finish that up. Let's finish that up. What are we saying? This is obviously the maximum, and this is the minimum. When we're talking about implicit differentiation, why do we never talk about x and y being related to a third variable? So we can take the derivative. Because in that case, this is really related to functions of several variables. And you're going to see that in Calculus 3. So we postpone that discussion to Cal 3. Yeah, so x and y being related to t, a third variable t. Exactly. And this comes up naturally in higher dimensions. So it's like you're treating the expression in x and y as a function of two variables, and both x and y are functions of yet a third variable t. So we can ask the question, what is dx dt? What is dy dt? Yeah, so all of this comes up naturally in Calculus 3. All right, let's move on. Let's move on to a new topic. Rolle's theorem. Cal 3 is not the same as differential equations. No. Cal 3 is going to be the extension of Calculus 1 and 2 to higher dimensions. So in Cal 1, you know, you do limits and the derivative. So we're going to extend that to higher dimensions, functions of several variables. Instead of y being a function of x, you have maybe z as a function of x and y, or w as a function of x, y, and z, and so on. And you extend the notion of limits, the notion of continuity, the notion of derivatives to higher dimensions. And as you may know, in Cal 2, we do the opposite. Instead of differentiation, we do antiderivatives. We're going back instead of going forward. Right? You start with the derivative and you ask the question, what function gave rise to that? So instead of going forward, you go back. And in Cal 3, you do that as well with functions of several variables. You do multiple integration, multiple integrals. But right now, Rolle's theorem, let f of x be continuous. On a closed and bounded interval AB, differentiable on the open interval AB, and equal at the endpoints. No, it's nothing scary there. It's just a natural progression. Right? I mean, Calculus 1 and 2 prepare you very well for Calculus 3. Nothing, and it's very nice. So f of x is continuous on the closed and bounded interval, differentiable on the open, and f of a is equal to f of b. Then there exists a c in the open interval AB such that what? F prime of c is equal to 0. And you know, I mean, Matt is saying that he needs Cal 2 for physics right now. That's the slight issue I have with being forced to take physics so early. If you waited until you had done Calculus 4, physics would be so much better. Yeah, it's called advanced calculus. Advanced calculus. Where instead, right, I mean, in Cal 3, you extend the notions of calculus to higher dimensions, and in Cal 4, you do calculus on surfaces. Cal 4 is the last one. So you do calculus on surfaces, and this has many, many, many very nice applications to physics. Let's draw a picture of what's happening here. What are we saying? You have a function continuous on the closed interval AB and differentiable on the open interval, and f of a and f of b are the same, right? So you start and end at the same value. 262 is Cal 3 for engineers. So I'm teaching that this semester. And Math 180 is a course I invented, which gathers all the nice topics, all where you see a bunch of nice results that you wouldn't see in that you wouldn't see unless you were doing an undergraduate degree in mathematics. I mean, Cal 4 is still a very low-level class. So what do we say? We're saying that you're starting and ending at the same value. Continuous, so you can graph it without lifting the pencil from the paper. And differentiable, so that there are no jagged edges, right? No cusps, no corners. Well, high-level class, 564, 565, 600 level. That's those are high value. Those are high classes. Cal 4 is 264 for engineers, or 314, or is it 315? Anyway, something like that for math. Still very low. So what we're saying is that the derivative has to be zero somewhere. Why is that? Rachel, it's a precursor, if you will, to the mean value theorem. And why must the derivative be zero? Well, your function is continuous, so it has to have an absolute max and an absolute min somewhere, right? And notice that right here, by Fermat's theorem, the derivative has to be zero. And right here, the derivative has to be zero. So either at the absolute max or at the absolute min, the function has to be zero. The derivative has to be zero. And that's the idea. I'm not going to prove it, but that's the idea. I'm not going to prove it. You have to break it up into a few pieces, and it's a bit messy. Not that messy, but yeah. Do we want to take an example? We do not. But this follows from us there. What Rachel was referring to, the mean value theorem, which is really an extension. Well, we'll see a few examples of roles and the mean value theorem. Mean value theorem is really an extension of Rolle's theorem. Let f of x be continuous on the closed and bounded interval AB, differentiable on the open interval, then there exists a C in the open interval such that f of b minus f of a over b minus a is f prime of c. Let's understand what this means from a graph point of view. Right, the mean value theorem differs in that the functions don't need to be equal to begin with at the endpoints, right? If they were, observe that if f of a is equal to f of b, this would be zero, and we would get the conclusion of Rolle's theorem. So you see that the mean value theorem is an extension. What the mean value theorem says, from a graph perspective, this you will recognize as the slope of the line joining the endpoints, right? This is the point A, f of a, and this is the point B, f of b. So the slope of the line joining the endpoints is the change in y divided by the change in x, exactly this. And this you recognize to be the slope of the tangent line at some point, C. So what we're saying is that there exists a value of C where the slope of the tangent line is the same as the slope of the line joining the two endpoints. Right, maybe here, maybe another one right here. But that's what the mean value theorem says. And let's prove the mean value theorem. We'll prove it because it's so nice and slick. It follows immediately from Rolle's theorem. So you see, Rolle's theorem is a special case of the mean value theorem, one where f of a and f of b are equal, so that this is 0. But it also, the mean value theorem also follows from Rolle's theorem. So they're in fact equivalent. And the proof is just coming up with a good function. What good function? F of x minus f of b, no, minus f of a minus x minus a times f of b minus f of a over b minus a. Consider this function. Since f of x is continuous and differentiable, and this is a polynomial which is continuous and differentiable, this is just a real number, and this is just a real number, then g is continuous on the closed and bounded interval AB and differentiable on the open interval AB, because it's made up of a function, which is all of these things, a polynomial, which is all of these things, and constant numbers. What is g of a? G of a is? How do we know f of x is differentiable and continuous? Well, that's the assumption on the mean value theorem. So I'm defining this g using this function f. And as people are pointing out, g of a is 0. What about g of b? Right, if you plug in a, this whole thing is 0, so that's gone, and you get f of a minus f of a, which is 0. For g of b, when you plug b into this, you get b minus a, which cancels with this one. And so you get f of b minus f of a minus f of b minus f of a. 0 again. Not undefined, right? We're plugging in b for x, not for a, b for x. And these are going to cancel, and we get 0 again. So g satisfies the hypotheses of Rolle's theorem. So by Rolle's theorem, there exists a C where the derivative of g is 0. And what is the derivative of g? The derivative of g, we'll differentiate each of these pieces. It's the derivative of f. The derivative of f of a, well, that's 0. Right? Because f of a is a constant, and the derivative of a constant is 0. Minus, this is a constant, and the derivative of x minus a is just 1. So the derivative at the point C, which is f prime of C, minus f of b minus f of a over b minus a is equal to 0. Bring this to the other side, and you're done. Yeah, interesting. Similar to linear approximation. Interesting. Yeah. There you go. So you see one good function, just one good function. Isn't that interesting? Where did I lose you, Matthew? All we did was, well, first of all, we defined the mean value theorem. We showed the graphical representation of what that means, and then we proved it. We proved it using Rolle's theorem just by defining one good function. One good function gives you the proof. And you know, that happens quite a bit in mathematics. The power of one good idea, one good function. How did we create G? Well, I mean, that's the obvious question. A does not become 0. Maxwell, I'm not sure what you're referring to. So, I mean, what I'm suggesting is the graphical representation of the mean value theorem. Mean value theorem tells you that there is a point where the slope of the tangent line is the same as the slope of the line joining the 2 points. That's what the mean value theorem says. Let's take an example. Consider this. Let's verify that this function satisfies the hypotheses of Rolle's theorem on the interval -2 to 2 and find all the values of c in the conclusion. All right, well, I mean, what do you know about this function? F of x is a polynomial, so continuous and differentiable everywhere. So in particular, on the closed and bounded interval and the open interval, respectively. Right? And what about f of -2? Well, that's -8. -8 is -16. Have I made a mistake? No, that's fine. So -8 is -16, plus 8 is -8, plus 2 is -6. And f of 2, 8 minus 8 is 0, -8 plus 2 is -6 again. Very good. So f agrees on the endpoints. So by Rolle's theorem, there exists a point C in the open interval where the derivative is 0. What is the derivative? The derivative, 3x squared minus 4x minus 4. Where is this 0? Does this factor nicely? I think this factors. 3x and x minus 2 plus 2, is that correct? This is minus 6x plus 2x is minus 4x. Looking good. Looking good. So when is this 0? This is 0 when x is 2 or minus 2/3. And the only value in the open interval is minus 2/3. We were guaranteed the existence of at least one value in the open interval. There it is. There could have been more. Who's to say? But there's at least one. And in this case, there was only one. So Rolle's theorem only works if the endpoints are the same value. Exactly that. Let's take another example. Verify that the function satisfies the mean value theorem on the interval 1 to 3 and find all the C in the conclusion. So C is equal to negative 2/3. Exactly that, Elizabeth. Convinced? If the mean value is true, does that mean that Rolle's theorem is true? Well, I mean, in fact, they're both true, right? In the sense that we can prove each of these. What I think you mean is that if a function satisfies the mean value theorem, does it automatically satisfy Rolle's theorem? It does not. It does not, because Rolle's theorem has an added condition that the functions have to agree on the endpoints. But if a function satisfies Rolle's theorem, then it automatically satisfies the mean value theorem. And in fact, the mean value theorem becomes Rolle's theorem in that special case. Let's consider this. And of course, you know f of x being a rational function is continuous everywhere it's defined. So it's continuous everywhere except at 0. So continuous and differentiable everywhere except at 0. So in particular, f is continuous on the interval 1, 3 and differentiable on the open interval 1, 3. You're far enough away from 0, there's no issue. The derivative is, of course, minus 1 over x squared. And the mean value theorem tells you right, so this function satisfies the hypotheses of the mean value theorem, so it must satisfy the conclusion. In other words, f of b minus f of a over b minus a must be f prime of c for some value c. In this case, what do we have? B is 3, so 1 over 3 minus 1 over 1 over 3 minus 1 has to be the derivative at some value of c. Let me know when you're back. Excellent. So we see that c has to be plus or minus 3, but in this interval, only one of them. Namely, positive root 3. In some cases, you get all the values of c that are in, right? But here, only one of them. Right? Let's take one more example. A very nice final exam question. Show that this has a unique real root. Exactly, right, Shamir? We can use the intermediate value theorem. This is the sum of a polynomial and an exponential, both of which are continuous. And differentiable on R, and thus so is F. So is the sum, right? And somebody's asking, what is a real root? Well, you know what real means. It means it's a real number. Root is like a root of a polynomial when the function is 0. So they extend the idea of root to functions in general. So a root where the function is 0, a 0 of the function. All right. All right. So, what's f of 0? You know what f of 0 is just by looking. 1, thank you. What's f of minus 1? F of minus 1? It's minus 1 plus e to the minus 1. Or minus 1 plus 1 over e. And this is somewhere between 1/2 and 1/3, right? For sure it's less than 1/2. So this is going to be less than minus 1 plus 1/2, which is minus 1/2. So it's less than 0. So you see what has happened, right? You have the number 0, which is between f of minus 1 and f of 0. So by the intermediate value theorem, there exists a c in the open interval minus 1 to 0, such that f of c is equal to 0. That is your root. The intermediate value theorem tells you there exists a root. There could be more than one. You don't know. I mean, the intermediate value theorem doesn't tell you that there's only one. There could be several. There's no telling. And instead of calling it C, why don't I call it A? It'll be better. There exists an A such that f of A is 0. A is your root. All right. So we've established the existence of a root, such that. ST means such that. So now let's suppose there are more than one root. So if you have more than one, you have at least two. Suppose you've got two different roots, A and B. Right? Two different roots where f of A is 0 and f of B is 0. Now, one of these is going to have to be bigger than the other. So either A is less than B or B is less than A. Let's do this case. The other case will be exactly the same. So if you have this, then apply Rolle's theorem. To the interval AB. In the other case, you will apply Rolle's theorem to the interval BA. Doesn't matter, it's going to be the same thing, right? If you apply Rolle's theorem, your function, which is continuous on the closed and bounded interval AB, differentiable on the open interval, and equal at the endpoints. What is the conclusion of Rolle's theorem? Then there exists a C in the open interval such that the derivative is equal to 0. Right? Rolle's theorem tells you that the derivative has to be 0 somewhere. But look at your function. What is the derivative of your function? This is your function, right? This is the original function we're dealing with. The derivative is 3x squared plus e to the x. You know that 3x squared is always bigger than or equal to 0. So this is bigger than or equal to e to the x. And you know the exponential is always strictly greater than 0. So it's impossible for the derivative to be 0. Contradicting Rolle's theorem, because Rolle's theorem tells you that the derivative should be 0 somewhere. So an assumption we made must have been false. And the only assumption we made was that there were two roots. That's it. That assumption must have been false. There cannot be two roots, so there can only be one. There can be at most one. But using the intermediate value theorem, we have already shown there's at least one. So there's at least one, there's at most one, there's exactly one. How are we doing there? Questions? Anybody? second line onwards. So from here, using the intermediate value theorem, you show that there is at least one root. But remember, the question wants you to show there's exactly one. So intermediate value theorem gives you at least one, and mean value theorem, or Rolle's theorem, gives you at most one. So it has to be exactly one. And Kamal here wants us to discuss this, right? First of all, from Rolle's theorem, the conclusion is that the derivative should be 0 somewhere. But look at your function, take its derivative. This 3x squared is always positive, right? So, and so is the exponential function. So this could be 0. So this expression is bigger than just e to the x, right? Because it's e to the x plus something that is greater than or equal to 0. But you know the exponential function is never 0, right? You know the graph of the exponential function. It's always bigger than 0. So the derivative is never 0, contradicting the conclusion of Rolle's theorem. So an assumption we made must have been incorrect, and the only assumption we made was that there were 2 different roots. So you cannot have 2 different roots. So there can be at most one real root, but as Matthew points out, using the intermediate value theorem, we showed there was at least one. So there's exactly one. How are we doing? Questions here? So using both the intermediate value theorem and Rolle's theorem is how you would answer this question. Exactly right. All right. Well, there are no other questions. Looks like a good place to end. Thank you all for coming. And we'll pick this up again on Friday. You guys have a good one. See you then.